Okay, I'll get started. I just wanted to begin with a quick announcement or quick reminder. If you've got any questions whatsoever on test one, or in particular any questions on test one grading, make sure you come and see. You can come and see me, or you can come and see your recitation instructor. So we're more than happy to review the grading or look at how to do better on the test. So make sure you take advantage of that. Any questions on that? Okay. Then I'll get on with class. Today we're continuing the story of magnetism. We introduced magnetic interactions, attractions, repulsions, last class. We introduced magnetic poles, south poles, north poles, last class. We introduced magnetic fields and field equation, last class. Most of this class is going to be applications, examples, illustrations of the magnetic field equation to get us used to working with the magnetic field equation. Specifically, this is our list of topics. The first item is actually to introduce the idea that there's two ways that we write the magnetic field equation. In one way, we write it in terms of the magnetic force that's created by a magnetic field on a moving charged particle. We met that last class. Another way we write the magnetic field equation is the magnetic force on an electrical current in a magnetic field. And that's another way of writing the field equation. I'm going to introduce it at the beginning of this class. But then we're going to get on with various examples of moving charges or electric currents in magnetic fields creating magnetic interactions, magnetic forces. And we're just going to look at a bunch of examples. We're going to look at the important case of circular motion of a moving charged particle in a magnetic field. We're going to look at another important case of the magnetic force on a straight wire in a straight current carrying wire in a magnetic field. And we're also going to look at the case of a current carrying loop of wire in a magnetic field and the interaction that it experiences. So that's the task for today. So let's just begin with this this more the bookkeeping item. I want to tell you that there's two ways of writing the field equation for magnetism. One we met and one we haven't yet met. But they're really just two versions of the same equation. The point is that we've talked about moving charged particles experiencing magnetic forces. Electrical currents are the motion, movement, flow of charged particles. So electrical currents should experience magnetic forces in magnetic fields also. Sometimes we think about a moving charged particle, and we're going to figure out the magnetic force on that. Other times we're going to be thinking about a collection of moving charged particles that we think of as an electrical current and figure out the magnetic forces on that. So the point is that there's nothing fundamentally different about a moving charged particle or a electrical current. Both of them are charges in motion. They're just different descriptions of charges in motion. In one case where you're focused on one charge, in the other case where you've got a swarm of charges. But in both cases, they're experiencing magnetic forces in magnetic fields. So I want to introduce that equation. And I've done that on this slide. This is the field equation from the last class. Upstairs here on the left in the title. This is the field equation I'm introducing in this class. Upstairs here in the title on the right. They're both field equations for the magnetic force experienced by either a moving charge particle or electrical current in a magnetic field. If you want to think about a picture, if you want to imagine the situation that gives rise, can be thought of in terms of these two field equations, maybe think about this picture here. These green crosses are indicating a magnetic field that's streaming in towards the screen, streaming away from you. There is a wire that's stretched from the left to the right in this region of magnetic field. It's bathed in this region of magnetic field. This wire is carrying electrical current. This wire has charges moving along the wire. There's just two different ways of thinking about the flow of the charge, the motion of the charge down the wire in terms of individual moving charge particles where they would have some charge and some velocity, or in terms of the current itself, the number of coulombs per second down the wire. So this equation here that we met last class, we could apply to this particular charge moving in this particular field to figure out the magnetic force that it individually experiences. Or, this is the new thing, we could apply this particular expression for the magnetic force in terms of the magnetic field, the field equation, on the entire current, the entire swarm of charges that are moving along the length of the wire. So the one on the left would apply to this single charge on the left. The one on the right kind of applies to the swarm of charges that we characterize by an electrical current. Inside the two field equations, so I reproduced them here. This is the one from last class. This is the new one from this class. On the right-hand side, in both cases, we see the magnetic field B, because that's what's creating the magnetic forces. So there has to be a field, magnetic field B, to produce that magnetic force. And then we see either this QV, which characterizes the moving charge, or this IL. I is the current, L is the length of this wire. That characterizes the collection of moving charges in that section of wire. And so this QV and this IL play the same sort of role as each other. They're both a characteristic of nature, a property of nature. They both describe the motion of charge. One, the individual motion of an individual charge, QV. The other, the collective motion of a collection of charges, that's IL. But they're both characterizing that same characteristic or property that experiences or feels magnetic fields and experience and feels a corresponding magnetic force. So they're playing similar roles here. We also see the sine thetas, if we remember. The funny thing about the magnetic field equation is the stuff on the right-hand side, the field and the moving charge particle or the electrical current, it has a direction to it. Both of those things have a direction to it. The field has a direction, the current or the charged particle motion has a direction to it. And this sine theta here accounts for the angle between those two directions. Anyway, so we'll be using both of these field equations in today's class, and we'll get some experience with them as we apply them to different situations. Just a word about the direction, the right-hand rule. So we learned this was a picture of the field equation. This time it's a picture of the field equation in the language of current, rather than in the language of a single moving charge particle. But whether it's the picture of the field equation for a single charge particle from last class, or it's the picture of the field equation for a collection, an entire current, in this class, we can picture the various directions that are in the field equation. So that there's the direction of the moving charge particle, or in this case, the electrical current. There's the direction of the magnetic field that's going to create the force, and then there's the direction of the force itself. And the right-hand rule for the current version of the field equation says that you would point the palm of your right hand, so here's the palm of my right hand, in the direction of the electrical current. That's the motion of the moving charged particle. So in the picture upstairs, it's from left to right. You would curl your fingers in the direction of the magnetic field that's bathing that current or that charged particle. So in my picture on the screen, I'm trying to draw the field going into the screen. So I would point my fingers going into the screen. The thumb would then describe the direction of the force, point in the direction of the force on that electrical current in that magnetic field. So it's the same right-hand rule because it's really the same field equation, but just cast in the language of current rather than a single moving charged particle. Okay, so let's get on with some examples now. I've got one example which is just about a single moving charged particle, and then I've got a couple of examples that are about, or a few examples that are about electrical currents. And so we're going to get experience with both versions of the field equation. So let's start with a single moving charged particle. And here's a very interesting thing, that a single charged particle moving in a magnetic field, specifically moving in a perpendicular magnetic field, a perpendicular uniform magnetic field. So it's bathed in this, the region it's moving in is bathed in this uniform in size, uniform in orientation, perpendicular magnetic field. That charged particle actually executes perfect circular motion. It's a way of creating perfect circular motion of a charged particle. Maybe it would be an electron, or maybe it would be an ion, or some sort of moving charged particle. And so I want to describe that motion. And first I was going to demonstrate. I can't quite demonstrate. I'll show you a picture of the circular motion, but I can show you kind of the curved particle motion, and then we'll see a picture of the circular motion. So I'm going to show this demonstration here. There is a source of electrical current that's on the left-hand side, and I'm going to switch this on. That electrical current creates it's actually amazing really, it's a stream of electrons that are streaking from the left-hand side of this tube to the right-hand side of this tube. And so this green band that you see here, this is actually a stream of electrons flying from the left to the right through some almost empty space in this tube here. It's not quite empty. There's a little bit of gas in here, and that gives it the green color. So you're actually seeing electrons flying at 1,000,000 meters per second from the left to the right in this tube. I've got a bar magnet. So I've got a bar magnet, and as you now know, the bar magnet has a north pole. Here's the red end, south pole, white end. There's magnetic field lines pouring out of the north pole. Can't see them, but they are. There's magnetic field lines pouring into the south pole. Can't see them, but they are. I'm going to bring up the bar magnet, and you see I can curve the path of the electrons. And if I bring up the other end of the bar magnet, I can maybe I'll turn the lights off for this. This will be better. That's not off. This thing is making a sound as if there's a little mouse in there. The mouse is running on a treadmill and powering this thing, but I don't know why it's making the sound. It's nothing to do with the demonstration. But anyway, I want to show you the curvature. As I bring the bar magnet up, I can curve the electrons upwards. I can curve the electrons downwards with the north and south poles. That's exactly what happens in the circular motion, except here I don't have a nice uniform magnetic field, and so I can't create a nice uniform circular motion. But we're going to see how that works. I do like to set the mood somehow by adjusting. Not too bright, not too light. Okay. So here's a picture of the situation that we're thinking about. We said we're going to think about a moving charged particle in a uniform magnetic field. And we said that we're going to discover that it executes perfect circular motion. Over here on the left is a region of uniform magnetic field. So these little green turquoise crosses are indicating that there's a uniform magnetic field, because they're equally spaced, that's heading in towards the screen. The crosses say it's going in towards the screen. Here, in red, we've got a moving, positively charged particle. And I'm actually showing you here the path that it executes in this magnetic field, this circular orbit that it's going to undergo in this magnetic field. So somehow the interaction of the moving charged particle with the uniform magnetic field is going to create this perfect circular motion. So how does that work? Well, let me just give you the idea to begin with, and then we'll figure out the equations after we got the idea. This is a moving charged particle in a magnetic field. So it is going to experience a magnetic force in general. The rule for the direction of the magnetic force, according to the field equation, is that it's going to be at right angles to both the velocity vector, describing the motion of the charged particle, and the magnetic field itself. And we could even figure out the direction of the magnetic field using the right-hand rule. And that's the first thing that we should do. We could maybe look at a couple of points here and figure out what would be the direction of the force. I'm going to start with the bottom. At the bottom here, that moving charged particle, let's see, it's going counterclockwise. So I would point my hand from left to right. That's the direction of motion. The field is going in towards the screen, so I'm curling my fingers in towards the screen. My thumb is pointing in the direction of the force on the moving charged particle. So this is indeed an upwards force towards the center of this circle. Then the moving charged particle moves around a bit and it gets over here on the far right of the circular orbit. So let's think about the direction of the force here. Now the motion has changed. Now that at that moment the particle is going vertically upwards towards the roof. So I'm going to point the palm of my hand towards the roof. The magnetic field's still in towards the screen, the board, so I'm going to curl my fingers inwards. My thumb is going to point in the direction of the force on that particle. And now that force has also changed direction because the motion changed direction. It's now towards the left. But it's again towards the center of the circle. And we could do it over here too. Wherever you do this, wherever you try this out, you would discover that the magnetic force is always pointing towards the center of this circle, towards the center of the circular motion. That magnetic force is actually providing the centripetal force that's needed for circular motion. And so that's the key understanding. Because of the relationship between the directions of the motion and the field and the force, the magnetic force tends to provide a centripetal force and tends to drive, accomplish circular motion of our moving charged particle. And so that's what's causing this circular orbit, is a magnetic force creating a centripetal force. If we want to go further, we want to ask questions like, well, how big is the circle? What's the radius of the circle? How does it depend on the speed that you go around the circle? How does the circular orbit depend on the mass of the orbiting particle, the charged particle? How does it depend on the charge of the charged particle? We'd want to answer all those questions, like you might want to answer those questions as if you were thinking about gravity and you're thinking about the solar system and you're thinking about the motion of the planets. We want to think about this orbital motion of this charged particle. How does it depend on all the properties, all the ingredients? Well, that I worked out over here. And it's a very interesting story, really. So my starting point upstairs on the right here is that the magnetic force, Fb, is providing the centripetal force, Fc. So that's the fundamental idea that we drew from the picture. Then I remembered back to 211 and the centripetal force, and I remembered the equation for the centripetal force in terms of the radius of the circular motion and the speed that we undergo the circular motion. I filled in the expression for the centripetal force, this guy here, mv squared over r. I remembered, because I've just been talking about it, the field equation. So I filled in the field equation for the magnetic force for a single moving charged particle. So it's QVB. It would be QV sine theta, but here I got this special case of a perpendicular field. So actually sine theta is sine 90 is 1. So I just filled in my understanding how centripetal forces work, how magnetic forces work. I get this equation here. And if we rearrange this equation, that's all I'm doing down here, rearranging it, we can learn about the orbit and how the circular orbit depends on all the parameters in this situation, depends on the characteristics of the particle, depends on the magnetic field, etc., etc. So I divided out one of the v's. You've got a v squared on the left, you've got a v on the right. So I got rid of one of those, and I rewrote the equation for v, the velocity of the circular motion, which is in this equation sitting upstairs here in the numerator, in terms of the radius of the circular motion, which in this expression here was sitting down here in the denominator, but I can lift it up to the numerator on the other side. I get this little equation here. So it's just rearranging things. That equation tells you a bunch of interesting stuff. So what does it tell us? Firstly, it says, supposing you were to change the magnetic field. Supposing we make the magnetic field bigger. Then if you make the magnetic field bigger, then, and nothing else changes, you're going to make the speed bigger. You'll go around the orbit faster. If you make the magnetic field smaller, then you're going to go around a given orbit, you're going to go around the orbit less fast. So it tells us that. It tells us something very interesting. This is probably the most interesting bit about it. That the relationship between the speed and the radius of the orbit depends on this ratio for the particle's properties. It's charge to mass ratio. So it depends on this ratio of the charge of the particle to the mass of the particle. So that governs the relationship between the size of this and the speed, so the radius and the velocity of a orbiting charged particle in a particular magnetic field. If we divide through by r, let's divide this equation through by r. If we divide through by r, that's the radius of the orbit, that cancels out the r on the right-hand side. It gives us v over r on the left-hand side, which is actually what we call angular velocity, if you remember back to 211. That's the radians per second of circular motion. It tells us actually, and this is the equation I'm most like of these, that the angular velocity is just given by this simple expression here. The angular velocity of a particle executing circular motion in a magnetic field just depends on the product of the strength of the magnetic field and its charge to mass ratio. So the magnetic field is the external thing that we're going to apply, and the Q over m is the characteristics. It's like the personality of the particle. You know, an electron has a certain Q over m, certain personality. A proton certain Q over M, certain personality. And so the frequency at which the particle will orbit simply depends on the characteristics, its personality, its charge to mass ratio, and the field that you've immersed it in. Here's a picture of circular motion of moving charged particles. This is a real picture of a beam of electrons in a perpendicular magnetic field. The electrons are injected in here, and in this uniform magnetic field, under this magnetic force that provides a centripetal force, they just execute this circular motion. And if you measure the velocity or the angular velocity of these electrons as they orbit this circular path, you find that it obeys these little formulas that we figured out. Depends on the charge to mass ratio, depends on the magnetic field that you've immersed them in. This effect is actually what saves us from cosmic radiation from outer space. Cosmic radiation is moving charged particles that are bombarding, heading towards the Earth. Those moving charged particles enter the magnetic field. They're like a rain. So imagine the Earth, there's this sort of, we know what normal rain is, it's water droplets from clouds. This is a much bigger scale rain. There's the Earth. This is a cosmic rain. It's coming down from, the galaxy and galaxies beyond. It's raining down on Earth. It's going to kill us all. But we're lucky. There's a magnetic field of the Earth. And those moving charged particles start to execute circular motion in that magnetic field. They can't stop themselves. They're moving. They've got charge. They're going to execute circular motion in that magnetic field. And so they all get tied up. They all get tied up around the magnetic field, around the magnetic field lines. So I drew a few of them here. I mean, where they're tied up depends on the particular charge to mass ratio, depends on the particular speed of that particular cosmic ray, but they're all stuck above the surfaces of the Earth, wrapping around the field lines. And so that's really the umbrella, the magnetic umbrella that saves us from this cosmic rain. Okay, let's look at a more quantitative example. So let's work through this example here. We've got a stream of particles, or actually here we're talking about we've got a single charge particle we're going to think about. We've got a single charge particle with a certain charge. It's 1.6 times 10 to the minus 19 coulombs, so it's electronic charge, and it's got a particular mass. It's 2.5 times 10 to the minus 26 kilograms. So I don't know what it is. It's some sort of ion, some sort of ion. And we're told that we do two things to it. Firstly, we accelerate it with an electrical field. Secondly, we're going to deflect it with a magnetic field. So we're combining electricity and magnetism a bit. And this pictured here. So here comes a moving charge particle, and then we're going to accelerate it. So that somewhere in here, it's not shown, there's an electrical field, an electrical potential that's accelerating the moving charge particles, like rolling down the electrical hill. And then it's going to be shot into a region of uniform magnetic field. Here's the region of uniform magnetic field indicated by these turquoise dots. This is coming out of the screen rather than going into the screen. It's uniform because they're equally spaced. And in that field, it's going to execute a nice, simple circular motion. And we're told a couple of things about the electric and magnetic fields in this situation, or the electric and magnetic situation that we've got here. The potential that we accelerated with was 250 volts. The magnetic field that we deflect with is half a Tesla. And we're going to put all that information together and figure out the radius of curvature of this particle's orbit. So we're going to figure out that. So let's see if we can do that. I'll do it on the document camera. And I started with a sketch, of course. This straight line here, this is my region of electric acceleration. And then this circular orbit here, that's my region of magnetic deflection. And so those are two regions where it's electricity doing the work or magnetism doing the work. I denoted the sketch with the magnetic field, half a Tesla, and the accelerating potential, 250 volts. And then I wrote down here that these are the properties of the particle. We said that in these magnetic deflections, for example, what counts is the personality of the particle, its charge to mass ratio. So I wrote down Q over M, Q and M. We want to know the radius of the orbit. The question is, what is the radius of this orbit? Well, we could figure out the radius of the orbit if we knew the speed of the particle. That's exactly the equations I was just talking about, the relationship between the speed of the orbital motion and the radius of the orbital motion. But we've not been told directly what the speed of the particle is. So actually, there's two steps in this problem. First, we've got to figure out the speed. That's the electrical part of the problem. Then we can figure out the magnetic force, sorry, the radius, the magnetic radius from the magnetic part of the problem. So I've got two parts of the problem here. The key idea for the speed is about energy. And the key idea is that when we accelerate that charged particle, what are we doing? We're rolling it down an electrical potential hill. We're turning electrical potential energy into kinetic energy. And we can figure out the speed, which reflects the kinetic energy, knowing the height of the hill, that we rolled the electric hill, that we rolled the particle down. All I got to do is to fill in the initial potential energy of the particle at the top of the hill, so it's PE subscript I, and I'll be able to get out the kinetic energy at the bottom of the hill. So just like a ball rolling down a hill, but this is a iron rolling down a electric hill. But still, I'm filling in the potential energy. It's the height of the hill, V, times the charge of the particle. So that's the potential energy that's lost by moving the charged particle, and that energy didn't get destroyed, it just became kinetic energy. So on the right hand side here, I got the kinetic energy. And if you look at this equation, we can rearrange this equation, right? We can rearrange it for we want the speed. So if I multiply by 2, both sides, I divide by m, I take the square root. That is an equation for the speed. I'm not going to fill in all the numbers. It'll take me 5 minutes. I'll probably write them wrong. You won't be able to read them. But I did calculate what this speed is. It's 57,000 meters per second. Okay, so now we got the speed. So that was kind of like part A of the problem. Now we know the speed at which the the ion is flying around this circular orbit. That's enough now, with our understanding of the circular orbit, to find out what the radius of the circular orbit is. Remember, we derived that equation that related the speed and the radius. It was that the speed of the circular motion equals Q over m, particle properties, times the radius of the circular motion times the magnetic field. I've just got to take that equation and rearrange it now. I want the radius, but I know the speed. And so if I'm going to rearrange this equation, I'm going to get mv divided by rb. Gosh. So that's rearranging the equation. where did my cue go? Yeah, thank you. This is ridiculous, what I just wrote down. Please don't tell anybody. I mean, first sign of lunacy, I think that was. There's been other signs, though. Anyway, we got an equation for the radius of the particle moving in a circular orbit. Everything over here on the right-hand side, everything I know. I know the mass, I know the speed, I just figured it out. I know the charge, and I know the magnetic field. So again, I'm not going to plug them all in, it'd take too long. But if you plug them all in, I got 0.0177 meters. So out of all those combinations of really big numbers like the speed and small numbers like the charge and the mass, I ended up with a kind of everyday radius of curvature, and that everyday radius of curvature was a little under 2 centimeters. And so that's the radius of this orbit. This diameter here then is 4 centimeters. This device, this problem, is a real device. It's used all the time. It's called a mass spectrometer. Often you use it not for they don't use it for calculating the radius based on the velocity. Rather, it's typically used, you can measure the radius, you can set the velocity, you determine the charge to mass ratio of particles using this device. And if you know the charge, you can use this device to measure the mass of particles. So it's a very valuable device for measuring the masses or charge to mass ratios of subatomic particles, of ions, for example, or electron or a proton or whatever. So it is a real thing. I'm feeling I have to justify it, but I mean it is a problem, but it is a real thing. Now I'm confused. Okay, want to move on to another example. So that was an example of moving charged particle in a magnetic field. Now we're going to talk about electrical currents in magnetic fields. The first one is we're going to think about a single kind of straight wire in a magnetic field, and we're going to explore that situation. And then we'll move on and think about a current loop in a magnetic field, a bit more complicated situation. So here's an example of a straight wire, or it was a straight wire, carrying an electrical current in a magnetic field. So let's just walk through the picture here. We've got a magnetic field. Look at the little turquoise crosses. They're going towards the screen. They're uniformly spaced, so that's a uniform magnetic field. So we've got a region of a uniform magnetic field. We're told that this wire is carrying a current. Look at the little maroon arrows here. The current, the conventional current, that's the direction that positive charges would move, is downwards here. So we've got charge flowing from the top. Well, we've got current, a current that's flowing downwards. If we were to think about the electrons in the wire, which have negative charges, they would be actually drifting upwards. So we could think about the current flowing down or the electrons going up. But anyway, the current is going down. The magnetic field is in towards the screen. And so those are two ingredients to create a magnetic force, a magnetic interaction. And we can figure out what the force on this wire is. What is the sense, the direction of the force on the wire? So again, I'm belaboring the right-hand rule, but I'm going to point my palm of my hand, right hand, in the direction of the current now. So the current is, what is it? It's down in this picture. So current is down. The field is going into the screen, so I'm going to curl my fingers of my right hand into the screen, and then my thumb will point in the direction of the force, magnetic force on the current. And that thumb is pointing towards the right of the room, and so that is a a force towards the right. That's one way of thinking about the force in this situation. Another way would be, you could think about the electrons if you chose to. Yeah, you can think about the electrons. The electrons were actually going up rather than down. So the electrons are going up. So I point my hand in the direction of motion of the electrons. I would then curl my fingers in the direction of the field, so that's in towards the screen. This would be the direction of the force on a positive particle. My electrons are negative, so they experience individual forces that are towards the right. So whether you thought about the electrons themselves or the current as a whole, you always get that the force, you have to, right? The force is going to be towards the right. It's equivalent, you can think of that force on the entire wire, on the entire current, as being the sum of all the little forces on the many billions and billions of electrons that are flowing in the wire. So either way that you think of it, you'll get a force that's towards the right. This is just the opposite case. If we reverse the direction of the current, that's reversing the direction of the electrons, keeping the direction of the magnetic field unchanged, still in towards the screen, you're just going to reverse the direction of the force. So reversing the direction of the current reverses the direction of the force. Reversing the direction of the motion of the electrons reverses the direction of the force. Nothing magical there. Let's look at an example of this. And this is an example where, again, I'll not just visualize or picture the directions in the field equation, but I'm going to use quantitatively the field equation. Let's work through this example. So what am I doing here? Good question. I have somehow, I've built an electrical circuit, here it is, in which I've got a battery, so some current's going to flow around the circuit. And that circuit has this horizontal wire in it. And this horizontal wire is immersed in a region of magnetic field. And so there's going to be a magnetic force on this horizontal wire. And in this question, we're asked to imagine, this is sort of an interesting situation. I've got this circuit, it's kind of hanging from the roof. It's got this horizontal wire that's hanging on these two supporting wires that carry current on the left and right. There's a battery at the top. We're told that I've arranged such a very special value of the current, a very special value and direction of the current actually, such that the magnetic force on that wire, and there will be a magnetic force because it's immersed in the magnetic field on the picture, exactly balances the gravitational force. So that wire is kind of floating. There's no tension in the vertical supporting wires on the left and right. There's no tension in those wires because that horizontal wire at the bottom is just quietly, mindfully floating there in space. And it's floating there in space, sort of meditating there, because there's a gravitational force downwards, but there's a compensating magnetic force must be upwards. And our task is to figure out what is the direction of the current that will accomplish that, what is the size of the current that will accomplish this, this floating, meditating wire. Okay, see if we can do that. We're told, I should stress, we're told a couple of pieces of information. The mass per unit length of the wire is 0.04 kilograms per meter. So we're not told specifically either the length or the mass. We're told, again, it's like a charge to mass ratio a bit. We're told this ratio of properties, the mass per unit length. We're also told the field that we've immersed the wire in. Okay, so let's first make sure we understand physically what's going on through understanding the direction of the current. It must be, of course, gravity is pulling the horizontal wire down towards the floor. It must be, therefore, that magnetism is lifting the wire up towards the ceiling. So the magnetic force and gravitational force must be in opposite directions. So I picture those two forces here by these, this green arrow and this blue arrow in opposite directions. They're balancing each other. This is a situation of gravomagnetic equilibrium. The gravitational force, magnetic force are equal and opposite one another. So since we know that gravity is down, we know that magnetism is up. Since we know that magnetism we can figure out the direction of the electrical current in this magnetic field. Now, I've indicated it here as from left to right. Let's check that. So again, whenever you think about your right hand in the future, think about it as a representation of the magnetic field equation. So the right hand is going to point from the left to the right because that's the direction of the current that I pictured on the screen. I'm going to curl my fingers of my right hand in towards the screen. I'm going to curl them in towards this. What am I doing here? Can I start that again? Okay, I want to start that again because it's. I'm going to curl my fingers. Yeah, somehow I was doing this. So I've got my. See, look, you have problems with the right-hand rule. We all, if we have to be honest, we all have certain problems with the right-hand rule. And I just had a problem with the right-hand rule. Okay, so I'm going to start again, and I'm going to point the palm of my hand towards the right in the direction of the current. So that's one of the ingredients in the field equation. I'm going to curl my finger in the direction of the magnetic field, so that's in towards the screen. That's the other ingredient on the right-hand side of the field equation. My thumb then points in the direction of the magnetic force. And so with a current that's going left to right, which is what I pictured on the screen, with a field that's going in towards the screen, I do indeed get a upward force. So this current left to right it does give the upwards force to balance gravity. If the current was going, the other possibility is the current going in the other direction, right? If the current was going from right to left, then I would be doing this awkwardly, curling my fingers, pointing my fingers towards the left and curling them in towards the screen. That's a downwards force, so that wouldn't work. So it has to be that the current is going left to right. Okay, so finally I managed to do that. I mean, ironically, the problem told us what the polarities of the battery were. And so obviously this battery is arranged such that current flows around this direction in the circuit. Now let's find the size. Okay, how big is this current? Well, how big is this current is just, now we're going to focus on the size of the gravitational force, the size of the magnetic force. They've got to be equal to one another. So the starting point is this equilibrium in which gravity's size, magnetism's size are equal to one another, not worrying about directions anymore. So just Fg equals Fb. I understand the field equations for gravity and for magnetism. So I'm just going to fill in the field equations. So mg, I'm now asking you to think of that as a field equation. G is the gravitational field. You're immersing a mass in a gravitational field. It's going to experience a gravitational force. The force is mg. And then over here in green on the right-hand side, this field equation for a magnetic force. If you've got an electrical current in a magnetic field, it's going to experience a magnetic force given by this field equation here. So just plugged all that in. The angle between the current, which goes left to right, and the field that goes in towards the screen is 90 degrees. They're perpendicular. So this is going to be this frequent case where this sine of theta is just going to be 1. Okay, so now we've built a relationship between the various parameters in this problem that's going to allow us to solve for the current. Now you might have been worried. You might have been worried that I didn't tell you the mass. I didn't tell you the length of the didn't tell you the mass, and it didn't tell you the length of the rod that was hanging in the magnetic field and the gravitational field. And you might have been thinking, well, I'm never going to be able to calculate the magnetic force itself or the gravitational force itself unless I know the length of the rod and I know the mass of the rod. And that's true. We can't in this problem, because we don't actually know what the mass of the rod is or the length of the rod is. We couldn't calculate what the gravitational force is, what the magnetic force is. But we can use the fact that we know they're the same strength, to solve for the current. And so if we start rearranging this equation here, I don't know m, I don't know L, but what I need to know is the mass per unit length, the mass to length ratio. And I find that the current is just the mass to length ratio times the ratio of the fields, the gravitational field to the magnetic field. And so this equation really is coming about from a comparison of magnetism and gravity, and just depends on the properties that determine the gravitational force and the magnetic force. That's the mass and the length of the rod, and also the ratio of the fields themselves, G and B. Every number here, right, we know. We can fill in the mass per unit length. That was 0.04 kilograms per meter. We can fill in the gravitational field. We can fill in the magnetic field, and if we do that, you get 110 milliamps, 0.11 amps. And so that's the magic current that floats the wire, without any tensions in the vertical cables or the vertical wires that were supporting the wire. Okay. So the last example I wanted to work on is a current loop immersed in a region of magnetic field. And we're going to look at the interaction of a current loop in a magnetic field. This is also, the straight wire in a magnetic field is an important situation. Special case, but it's an important situation. For example, the electrical wires that carry the electrical current to your home that are strung between pylons across the farmlands of wherever, they are current-carrying wires in uniform magnetic fields. They experience magnetic forces. So that's a practical example of a current-carrying wire in a magnetic field. And when they build the pylons, they have to worry about the magnetic forces in the Earth's magnetic field. This example here of a loop in a magnetic field turns out to be a very practical, important example. And so that's why we're exploring it. I'm not just randomly picking examples. Well, sometimes I am, but not in this case. It is important. Okay, let's demonstrate this. Okay, I have a power supply, and I have a switch, and the terminals of the power supply pass through the switch. It's a special three-way switch. If I pull the switch towards you, the current will go one way around the circuit. If I turn it the other way, the current will go the other way around the circuit. The wires are then connected to these two vertical posts, conducting posts, which are connected to this copper loop here that's balanced upstairs here. Beneath the copper loop, this is quite a story, is a magnet. So this copper loop right now is immersed in a magnetic field. There's the south pole at the top, north pole at the bottom. So you can imagine sprouting out of the north pole of field lines, and they're looping up and heading back in the top. So there's some sort of magnetic field in the region of the copper loop. Right now, that copper loop is perfectly balanced there. It's just balanced with just a right amount of copper over there on the left-hand side to balance this amount of copper on the right-hand side. So it's just sort of sitting there balanced on that kind of pivot. And what we're going to do right now is there's no magnetic force on it because there's no current flowing in it. But if I was to flip the switch and drive a current around the circuit, then there would be a magnetic force on it because there would be a current in a magnetic field, and we just want to explore what that force would look like. And so let's do that. I'm just going to move the switch forward. So this is going to send the current in one direction. I don't know how it's wired up, so I don't exactly know what direction it's going to go. And we see it's now repelled by the South Pole. And again, if I move it forward, I mean, it's not hugely dramatic, but it was repelled by the South Pole. Then it's pulled back down by gravity. And then actually I can give it another kick. If you've got half an hour, you can just stand here, and every time it comes up, you give it another kick by sending a current through it. And then come up again, give it another kick. There's gravity pulling down. Now I'm going to give it another magnetic kick. And you can just, I mean, I could do this forever, really. Not ever, but. So we saw it was repelled by the South Pole in that case. I'm going to try and settle it down. It's very hard for me to settle this thing down. Now I'm going to send the current in the opposite direction. So if I send the current in the opposite direction, same magnetic field, you'd expect the forces to be in the opposite direction. And so we'd expect, we saw it being repelled by the South Pole. Now it's going to be attracted. And you see that, look, it's being attracted. I'll let it swing up. Attract it again. I'll let it swing back up. It's trying to balance itself. Then I'll attract it again. And again, if you do this like, you know, when we went on the swings when we were kids, and my mum and dad is pushing me on the swing, and if they time it right, you know, they can make me swing really quite high. And I could do that. But anyway, so this is an example, I'm getting off track severely. This is an example that this current loop experiences a magnetic interaction in a magnetic field. So this is a loop of wire rather than a straight stretch of wire. So we've seen a new effect, a new phenomenon here, and we're going to explore that sort of more theoretically through a problem, an example, an illustration. Let's see. So here's the problem that I want to explore quantitatively. It's simpler than this circular loop in a non-uniform field. Now I've got a nice rectangular loop in a nice uniform field. That's the big difference that will simplify the problem for us. So I want to, on this slide, examine the forces that are acting, the magnetic forces on the loop. And then on the next slide, we're examining what those forces do to the loop. How do they affect how do they move the loop? Let's take a look at the picture first. There's quite a bit of information on the picture, and then we'll turn the picture into some equations for the forces on the loop. So in gray here, this is the rectangular loop. So it has a certain width. It's called A on this picture. It has a certain height. It's denoted B on this picture. And there's a current flowing around this loop. Somehow we've driven a current around the loop, and it's going counterclockwise. So here goes the current around the square loop. We've immersed that loop in a magnetic field. The magnetic field is streaming from left to right. So here's some of the field lines in this turquoise here. And these field lines are kind of streaming across the face of the loop. Now, that loop we could describe, this is going to be important to us, so I'll mention it here. We could describe its its surface by a vector A representing the area. We've done this before. So that's what this vector A is. It's describing the area enclosed by the loop. It would have a size that is the width of the loop times the height of the loop. It has an orientation that is perpendicular to the face of the loop. So this dot here is meant to be showing you that the area vector describing this loop is coming out of the screen towards you. Anyway, what we effectively have is 4 sections of wire that make up the loop, the top, the bottom, the left and right, that are immersed in a magnetic field. Well, straight wires in a magnetic field is exactly the problem we were just working on. We talked about it in words, we solved a problem with it quantitatively, so we can apply the left side, the right side, the top and the bottom, straight wires carrying a current in a magnetic field. We can apply what we learned in the last example, last illustration. So let's do that. Let's ask the question, what is the force on the left? What's the force on the right? What's the force on the top, and what's the force on the bottom? Those 4 pieces of the current loop, and then we can think about the overall force that's acting. Okay, maybe we'll start with the top and the bottom. On the top, in our picture, the current is going opposite the direction of the magnetic field. The magnetic field's going towards the right, the current's going towards the left. On the bottom, the current is going precisely in the direction of the magnetic field. So the field's going towards the right, and the current is flowing towards the right. Remember, those are 2 special cases. So if you've got a charged particle and it's moving in the direction of the field lines, or opposite the direction of the field lines, i.e. along the field lines, it experiences no force whatsoever. Very strange situation. It's the same thing for currents, which are just collections of moving charged particles. If the current is flowing along the direction of the field lines or opposite the direction of field lines, there's going to be no magnetic force on that current. Now, you could see that literally through the field equation, that F equals ILB sine theta, because sine theta for those 2 geometries is either 0 degrees, 180 degrees, and sine of 180 is 0. Or you could just remember, look, if I got a current in the direction of the field lines, opposite direction of field lines, i.e. along the field lines, there's going to be no magnetic force. And so straight off, without too much, without any mathematics, there's no current upstairs here on this piece. There's no force upstairs on this section of wire. There's no force downstairs on this section of wire. We've only got to worry about if this force is on the left and the right. Okay, so let's start with the left. On the left, the current is going down. So I'm going to point the palm of my hand downwards. And the magnetic field is going towards the right. So I'm going to curl my fingers towards the right. Oh, my thumb is pointing towards you. That means that the magnetic force on that current in that field is towards you. So I've indicated that on the sketch here. This dot means that this is a vector coming out of the board towards you. And so there's a force over here that's towards you. For the right-hand side, similar idea really. It's just that now the current is going up. The field is going still the same way, towards the right. My thumb is pointing away from you and towards the screen, and so that's a force in towards the screen. And so I indicated that, as we usually do. This is a force vector that's pointing in towards the screen. That's what the cross means. So these are our 2 forces, I call them F1 and F2, that are on the left and on the right. One's out of the board towards you, and one's in towards the board. Yeah, question? Was that? Oh, you're doing the right-hand rule. Excellent. I hope you do it better than I did. Okay, so we got these 2 forces that are acting on the current loop. I've even written down the size of them, right? If I actually apply the field equation, I can write down the forces here. Now, let me just explain a little bit when I wrote them down. So that equation, the field equation, is ILB sine theta. who's n? Who's n? N was, this is a loop of wire, it's n turns of wire. So this current is flowing around n turns of wire. It's if the total current is Ni down any length of wire. So just to make this a more general problem, because we often have loops that are made of many turns of wire, many loops of wire, one on top of another, the current here down one arm, the left arm or the right arm, if you've got n turns, is the current I in each turn added up for the n terms. So it's going to be Ni. So the Ni is just the total current that flows down the left, total current that flows up the right. And I've just incorporated that in this equation here. The other thing I built in is the fact that the sine theta is the current is going down or up, the field is going left to right, and so there's 90 degrees between the direction of the current and the direction of the field. And so sine theta is sine 90, which is 1. Okay. Well, we learned an interesting thing there, that there's two forces on this current loop. And I've redrawn the loop here. This is a helicopter view. So I've gotten in my little, climbed aboard a drone. And I flew above the current loop. And I'm looking down on the current loop. So in this picture, the magnetic field is still going left to right, but I'm looking down on the top of the current loop. I'm seeing current coming up on one side, going down on the other side. I see these forces that are acting on the current loop, F1 and F2. What are those forces going to do? Well, the net force is actually 0 because one's up, the other one's down, they're equal size, they cancel each other out. What they actually will do is tend to turn or rotate or torque the current loop. They're going to create a rotation of the current loop. It's not going to undergo translational motion because the forces balance one another. It is going to undergo rotational motion because the torque of this force and the torque of this force don't balance one another. They both tend to turn it in this picture, right, clockwise. And so we're going to get a torque. Now, I've not, in the book, it actually derives for you what the torque is in this situation. I've just written down the equation for the torque. The important thing is you've got two forces, both creating two torques. Those two torques superimpose to create a net torque. That net torque is given, is tau, is the symbol, is given by this expression here. There's a bunch of things in here you wouldn't be surprised to see. Look, it depends on the magnetic field. More field, you're going to get more torque. Depends on the current. More Ni, that's the total current. More Ni, more torque. So that makes sense. What's this A here? This is the area of the current loop. It's in proportion to the area of the current loop. Why does it depend on the area? There's two factors to that. Firstly, the force is bigger if the lengths of the sides that were experiencing the force were longer. So, you know, if the height of the loop was greater, then you get a bigger force. But also, in the other direction, if the loop is wider, then the same size force creates a bigger torque because the force is applied further from the axis of rotation. So those two factors actually mean that the torque itself depends on the area that's enclosed by the current loop. All these three things over here, you can write in terms of one quantity. It's given this symbol mu. It's called the magnetic dipole moment. It's equal to Nia. It characterizes the size and the shape and the current that's carried by the loop. The only other factor is the magnetic field. So we end up with this very simple conclusion that this loop will rotate, and it will rotate with a rate that's determined by the field and its magnetic moment, where its magnetic moment depends on its area, how big or small the loop is, depends on how many turns the loop has, how many turns of wire, and depends on how much current you push through the turns of wire. So it depends on all those things. This is a more general version of that torque that is experienced by a current loop. The only extra thing in here is a sine theta. This sine theta is the angle between the field, the magnetic field B, and the area vector A that described the loop. In the prior example, if you remember, I started with a special geometry. There was 90 degrees between A and B, between the orientation of the field and between the magnetic field. In this particular case, I'm just writing down the equation with the extra sine theta, which is the general case, when there isn't 90 degrees between these two vectors. If we put in 90 degrees, we get the equations from the prior slide. But if it's not 90 degrees, we get a lesser torque, a smaller torque, that depends on this angle here. But still, you've got the magnetic moment times the magnetic field, now times this sine theta factor. That determines the torque that's going to rotate the loop. Okay, let's look at a quick quiz here. Do I want to do this? I think I'm running out of time. So I think I just give everybody credit for the quiz. I will do that. But take a look at the quiz. And I will just do, in this last few minutes, I just want to show you this one concrete example of calculating a torque. So I'll credit everyone for the quiz. And let's just talk about this in these last few minutes, this example. Here we've got a current loop in a magnetic field, and we're told the current that's flowing in the loop, we're told the size of the loop, and we're told the magnetic field that the loop is immersed in. And we're asked to figure out what the torque on this loop is. So remember, the idea is that this loop in this field will experience, in general, forces on the sides of the loop. Those forces, whilst they do add up to make total net force, they add up to make a non-zero net torque. So this is going to rotate in this magnetic field. That's what we saw this device doing. It rotated in the magnetic field. That's what we saw. No, we just saw this one, sorry. So this rotated in the magnetic field, and this will rotate in the magnetic field. And we're going to figure out numerically here the torque. So let's do that. Now, the key things that we're told in this problem are the field. Obviously, we've got to be told that the magnetic field is 0.8 of a Tesla. So that's important. We're told some information about the loop, the current loop. We're told this one has a single turn, n equals 1. This one has a certain radius. It's a circular loop, has a certain radius, 32 centimeters. We could figure out the area of this loop, be pi r squared, pi 32 centimeters squared. And we're told the current flowing in the wire of the loop. Those are all the ingredients of that quantity that I introduced, mu. That was the magnetic moment. That was given by NIA. In this first sentence here is basically listing those three quantities. N is 1, I is 17 milliamps, and A, well, A is pi times 32 centimeters squared. So we've been told the magnetic moment. We're then told the magnetic field, but we put the magnetic moment in, and we're asked to figure out the torque. All we've got to do is multiply out that magnetic moment with that magnetic field to find the magnetic torque. So let's do that. Here I am doing it in 2 steps here. So firstly, we want to figure out, this just, I mean, you could do this in 1 step, but to me it's convenient. I kind of like the understanding to first figure out the magnetic moment and then figure out the torque. Magnetic moment, NIA. Number of turns, what do we say? It was 1. Current, what do we say? It was 17 milliamps. That's 0.017 amps. Area of the loop. It was a circular loop. We're told the radius. the area of the loop is pi r squared. So it's pi times 0.32 meters squared. Multiply all this chain of things together, I got this number for the magnetic moment. Its units are amps meters squared. It's about 5.5 milliamp meters squared. So that's the magnetic moment. That is just the property of the loop itself, a characteristic of the loop itself and the current it's carrying. We now dropped it, bathed it, immersed it in a magnetic field. It creates a torque. The magnetic field creates forces, which creates torque. The torque is given by this little equation here. I fill in the magnetic moment, I fill in the strength of the field. They're orientated such the vector A of the loop and the magnetic field vector V are at right angles to one another. I put that in and I get the torque. And so that's an example of calculating the torque. This is the third case that we looked at. Just to summarize,